Hi everyone, and welcome to our video on finding nth roots of complex numbers. So what we do is use Domovs theorem. We just need to convert it a little bit. So for instance, when we have our complex number, z equals r cosine of theta, let's put a pause on theta for a second. So in all of our problems, we just take the quickest angle from 0 to 2 pi. And it works out just fine. However, you could have found coterminal angles and worked the problems in similar ways to get the same answers for different things. So what we will do in this case, though, is mention, yeah, we do need the coterminal angles in this problem. So plus 2 pi k to that. And then we'll do it to the sine portion as well. Theta plus 2 pi k also. Again, these two angles are always the same. And then as a reminder, our Domovs theorem, I'll just put that to the side, tells you if you raise your z to a power, it raises r to the power, that's n, and then it multiplies the theta. Oh, and I'm running low on room. Let me move it over just a little bit. Actually, let me put it over here. So here's our Domovs theorem. Raise the r to the power, and then multiply the angles by n. Okay, so there was Domovs theorem from the last video. And so it's in our scenario, what we have is still a power, except it's a root, which means it's a fractional power, which really doesn't change the scenario. So our r is still getting raised to a power, so just like that. Our theta is still getting multiplied by the power. Okay, so multiply by the power means the n is in the denominator, except now instead of just theta, we are saying, well, we should keep it as a coterminal angle right here and here. Okay, so I'm marking it up quite a bit, but that is our theorem that we'll use when we have to find the nth roots of something. Okay, so when finding roots, we need to make sure we have the plus 2 pi k. That's the only case we need it. Okay, so and we'll see why very soon. Okay, so let's break this down. Okay, but still you can kind of think, oh, it's just like Domovs theorem with a minor tweak. Okay, so let's find the fourth roots of this complex number. So that is the complex number z that they're giving us. And then just like all other problems, we really want it in polar form. Okay, so 8 to the right and then down 8 radical 3 is something like that. Now this is one of the special right triangles. I'm going to go ahead and speed it up a little bit to state our r would be 16. Okay, so it would be doubling the smaller part of the right triangle. Okay, so there's our right triangle getting in. And we could find theta. Okay, so and if we don't know it's a special right triangle, we could do Pythagorean's theorem. And we could also use tangent to get this angle. But because it's close to the y-axis, and I know it's a special right triangle, we know it would be theta is 5 pi thirds. Okay, so we've got our information there, which means I can now rewrite z using 16 and then cosine of the angle, 5 pi thirds, plus I sine of 5 pi thirds. Okay, so that's how we normally do it. But again, we're finding a root. So that means I need to add 2 pi k to the angles. And then now let's rewrite it. Okay, so I would have z is equal to 16 cosine of 5 pi thirds plus 2 pi k plus I sine of 5 pi thirds plus 2 pi k. Okay, so it looks something like this. All right, so we've got our big old scenario set up there. And then now I can start to divide by the, or not divide, let's put in our radical. Okay, so now what I've got, we are finding the fourth root. Okay, so I'm going to modify this and say, well, this goes, that's the fourth root, 1 over 4. So that means the 16th needs a 1 over 4. And then our angles right here need to get divided by 4. There we go, and I'm just modifying it. Good to go. Okay, and then these angles, okay, so again, it's kind of like a little bit of scratch work that's occurring with it. Okay, so to the side, with my scratch work, I have 5 pi thirds plus 2 pi k over 4. Well, what I would do in this scenario to simplify is I see my small denominator is 3. So I would multiply the whole numerator by 3, the whole denominator by 3. That 3 in the numerator distributes. And so what this angle becomes is just 5 pi plus 6 pi k. And then 4 times 3 down below is 12. Okay, so that's what this angle now is. Okay, so let's see it. So let's rewrite it. So my z to the quarter, 16 to the 1/4 we can do as well. That is just 2. So the fourth root of 16 is 2. And if we don't see that, I'm going to erase this scratch work. Okay, so my scratch work, we could just break down the prime factors. So 16 is 4 and 4. And then 4 is 2 and 2. So that's why. So 2 to the 4th is 16. So that means this fourth root of 16 must be just 2 then. Okay, so that's where that comes from. Let me erase that though so that I have enough room. Okay, and what we did is we also changed our angle. That's that scratch work to the top right there. 5 pi plus 6 pi k over 12. And again, that's the same angle for both cases. 5 pi plus 6 pi k over 12. Okay, so there's our big setup. Okay, and then now what we're doing to find all of these roots is we're going to let k equal 0, k equal 1, and however many we might need. Okay, so 4 roots means we should have 4 answers. So it should just be 0, 1, 2, and 3. Okay, so the number of answers we need is the number of k's that we need, starting at 0. So 0, 1, 2, 3. All right, so let's plug those in. Okay, so for k equals 0, we are going to get 2 cosine. So if we plug k equals 0 in, that is 5 pi 12ths. Oops, let's go ahead and do, I forgot the parenthesis, that's why it's weird. Okay, my first parenthesis in the wrong spot. 2, big parenthesis, there we go. Cosine of 5 pi 12ths plus I sine of 5 pi 12ths. Okay, and since that's not on the quoted unit circle, we'll leave it as is for now. So that's one of them. Okay, and then for k equals 1, the way that I usually do this, so for k equals 1, I'm now just going to add whatever that angle is, or the numerator part, to the 5 pi. I just count by that. Okay, so instead of actually plugging it in and doing it all, I'm just going to say it's 2, big parenthesis, cosine. Add 6 pi to 5 pi, so that'd be 11 pi 12ths plus I sine of 11 pi 12ths. And then 2 more for k equals 2. Again, I'm looking at my previous answer, the 11 pi 12ths, and I'm just going to add 6 pi to the numerator part. So it'd be cosine of 17 pi 12ths plus I sine of 17 pi 12ths. And then one more time, k equals 3 would be 2. Cosine, again, one more time, add 6 to it. That would be 23 pi 12ths plus I sine of 23 pi 12ths. There's our other 4. Okay, so I've got them all here, or our other 3 to make 4 total. Like that. Notice if I added another 6 pi to the numerator, that would have been, okay, to the side, it would have been 29 pi 12ths. But getting a coterminal angle, that would be back to 5 pi 12ths. Okay, so that would be the same answer. Okay, so we wouldn't want that. We wouldn't want a repeated answer. Okay, so that's why we stopped at k equals 3. Okay, so once you start getting repeated answers, you've gone too far. All right, so it does say to graph these numbers on the complex plane. The 5 pi 12 makes that a little harder. I mean, these would be weird numbers anyway. So what I'm going to do is just kind of do a quick sketch still and just kind of make sure the angle's good. So 5 pi 12ths would be somewhere about there on our angle. Okay, and then the radius is 2, so somewhere maybe about there is what we'll say. And then 11 pi 12ths, notice that's very close to pi, so that would be something like that. And then still a length of 2, so I'm trying to make that the same distance. And then 17 pi 12ths, that's very close to 3 pi halves. That would be somewhere about there, we'll say. And then the last one, 23 pi halves, is very close to 1. Or very close to 2 pi, I mean. Which is somewhere about there. Okay, so, and, oops, 5 pi 12ths was not in the middle. Oops, that one's way off. Sorry. 5 pi 12ths is close to pi halves. So something like that. Sorry about that. Okay, so there is the 5 pi 12ths angle. Here's the 11 pi 12ths angle. Here is the 17 pi 12ths angle. And there's the 23 pi 12ths angle. Okay, so what we wanted to do with this, so I really just wanted to get the angle involved. And then I am going to just kind of try to connect all these with a circle. It should be nice and symmetrical. Okay, so notice all of these rays are looking like it's symmetrical around. That's what's going to happen with these problems if we were to graph it. So that was the only reason to see the full graph of it. Okay, so there they all are, sketched out. Okay, anyway, let's finish this off. Okay, so our last one, the z to the 5th plus 1 equals 0. So it's a solve problem. Okay, so that means we've got z to the 5th is equal to negative 1. And then now what we need is the 5th root to help us along with this problem. Okay, however, we don't really want this. We again want to convert this into polar form and then proceed through like we did on the last problem. So convert negative 1 into polar form so that we've got, let's go ahead and sketch that. So negative 1 is over here in polar form. Okay, so that means its radius is 1 still. And the angle is pi. Okay, so negative 1 in polar form is 1, big parenthesis, cosine of pi. But let's go ahead and instantly say, well, we're going to take a root. So let's make sure we just do plus 2 pi k right away. And then plus I sine of the same thing, pi plus 2 pi k. Okay, so there's the negative 1 getting converted. Okay, so again, what we wanted, so over here on the left, notice the 5th power and the 1/5 would cancel. And then we said, oh, that should be raised to the 1/5 then. However, we need it in polar form so that we can see all of the answers. So that means this 1 would still get raised to the 1/5 power, but our angles would get divided by 5. There we go. So there's our big setup. Okay, so our z then in this problem, again, we're going to let k equal 0. Okay, so this is for k equals 0 now. So this one's at least set up a lot faster. 1 to the 1/5 is instantly 1. And then if I let k be 0, I would have cosine of pi fifths plus I sine of pi fifths. And then keep it going. Okay, so I need 5 answers because that's the 5th power. So the 5th root, I should have 5. So we would need to go to k equals 4, it looks like. So my next answer, again, 1 to the 1/5 is instantly 1. However, this time around, again, all I'm doing is just going to add my coefficient there. So if k is 1, I mean, that is left over with 2 pi, and then add it to the pi value. So I would have cosine of 3 pi fifths plus I sine of 3 pi fifths. And then keep it going. Okay, so k equals 2. Z equals 1, big parentheses, cosine. Again, just continue adding 2 pi to the numerator. That would be 5 pi over 5 plus I sine of 5 pi over 5. Okay, notice that would simplify, but let's keep moving so we can continue the pattern. And then if I let k equals 3, I would have z equals 1. Still add another 2 pi to the numerator, would be 7 pi over 5 plus I sine of 7 pi over 5. And then one more time where k equals 4. I would have 1 and then parentheses cosine. Again, add 2 pi to that would be 9 pi over 5 plus I sine of 9 pi over 5. And there we go. Notice again, if I were to add, so a little bit to the side, if I added another 2 pi to the numerator, I would have 11 pi fifths, but that is coterminal with pi fifths. Which means I already have that answer marked. Okay, so we don't want that one. Okay, so these are all unique angles except once I start repeating if I were to keep going. Okay, so there we go. So these are our answers in polar form. Now the middle one we would simplify and just say pi. Okay, so this middle one, 1 and then big parentheses cosine of pi plus I sine of pi. Notice this one we could do. It does simplify to be just -1. Okay, so and that makes sense. -1 to the 5th plus 1 will equal 0. So we can check that answer pretty quickly. These other ones would also work. So what this is saying is if I wanted to check that first z that we found, it's saying, well, if you plugged in cosine of pi fifths plus I sine of pi fifths, raised it to the 5th, and added 1 to it, it will be 0. Okay, so we can use Domovs Theorem to show that it will work. Okay, so it will be a correct answer. So will all of these others. Okay, so there we go. So it's kind of using our rules for polynomials, going back to pre-calc 1, going back far, and knowing that whatever the power is the number of zeros we should have. There should be 5. Or it's whatever the root is. So on this first one, the root was 4. So we should have 4 answers. Okay. One last thing. If we wanted to, I mean, we could sketch all those angles out to see the symmetry. Okay, so pi fifths, somewhere maybe about there. Okay, so bigger than pi sixths, smaller than pi quarters. 3 pi fifths is somewhere probably about there. 3 pi fifths. Pi is this one. 7 pi fifths is down there. And then our 9 pi fifths would be over here. Okay, so we can start to see, oh yeah, these are, it's like making a starfish. Okay, so those should be all nice and symmetrical looking. Okay, anyway, but that's it. Okay, so finding the roots is really kind of just like Domovs Theorem, except just make sure to do the plus 2 pi k, and then, well, a lot more extra actually. Okay, so these ones take a little bit more time. Okay, so be patient. Okay, but otherwise, that's it. So if you do have any questions, please let me know. Otherwise, thanks for watching. That's it. See you next time.